So right now, look how long the force of friction is, how long the arrow is. Okay, and then how long is that arrow now? That's a lot less. So the frictional force after the object starts to move is less than when it wasn't moving. Okay, so the frictional force after it moves is called kinetic friction, and the frictional force before it moves is called what? Well, it's not kinetic friction. We only had two different types. But I think that what's interesting is that we saw that as soon as we went from not moving to moving, the friction force changed dramatically and it changed instantaneously. So we went from static friction to kinetic friction. But what this brings us to is that static friction has sort of a maximum value. Once you get past that maximum value, the object's going to start to move. And when it starts to move, our kinetic friction is less than our static friction. So that's interesting. So it is easier to keep an object moving when there's friction involved than it is to get that object to start to move. All right, so question 5, making sure that the sum of forces is checked above. What was the sum of forces? Why is the sum of forces or net force less than the applied force? Think about the direction of forces in your answer. All right, so let's go ahead and check sum of forces, and we're going to do it one more time. All right, sum of forces got unchecked for some reason. Okay, and let's go ahead and see it move. So the sum of forces to the right, and when it was to the right, it was less than okay, so let's take a look. All right, the sum of forces is to the right and it's less than the applied force. So why is that the case? Well, why? Well, remember, whenever we have a vector diagram and we have two arrows pointing in opposite directions, we subtract, and two arrows pointing in the same directions, we add. So it is less than the applied force because the net force equals the applied force minus the force of kinetic friction. Okay, and of course write this in your own words, and we're always using two sentences per answer. So and remember, we do subtraction because the direction of motion, so the direction of the forces tells us to what? To do subtraction. All right, 2 more steps. We're going to change the surface to ice. Let's press reset before we do that though. Okay, so reset, then go to ice. After that, we're going to slide the applied force slider bar until the box starts to move. Okay, so remember before, when we tried to move the slider bar, the force of friction increased. It was a static force of friction until the applied force got to such a great value that the static friction couldn't keep up and suddenly we were moving to the right. Okay, so let's see what happens if we were on ice, which has a low coefficient of friction. All right, so we immediately started moving to the right. There is no frictional force whatsoever. So that's interesting. Okay, so if our object is really slick, or it's on a really slick surface, and there's no friction as determined here, then you're immediately going to accelerate in the direction of the applied force, which is to the right. Okay, so there simply is no there is no static friction. It's as simple as that. Nothing to oppose motion. Okay, and so the next part is, so very quickly, let's just talk about what we've seen so far. So we saw that static friction is the friction that keeps an object from moving. If you say try to push a heavy crate or some furniture across the ground, why won't it start moving until you get a really strong force? Well, that static friction is, remember, friction always opposes the direction of motion. Static friction will essentially oppose your push until your push is so great that the static friction can't increase any further. Okay, and so there's a limit to the static friction, just like there's a limit to the kinetic friction. And so what are those limits? Well, in order to calculate them, we need to know some equations. We have the static friction force is equal to the coefficient of static friction. This is a material property, so the roughness of the surface, times the normal force, and that's equal to m times g. And so remember, the normal force, that's Fn on the screen, so this Fn right now is the normal force, that's equal to the force of gravity. And so what is the normal force? Well, remember, why are you not sinking into your chair? Why are you not sinking in the ground right now? Well, you don't have any vertical velocity, and the net force on you is zero vertically, meaning you're not moving downwards because the force normal is equal to the force of gravity. Okay, and so we think of that for all of these problems with two objects, an object sliding on another object, the force normal is equal to the force of gravity. That's m times g. G is the acceleration due to gravity. Okay, so we have our two equations, one for static friction and one for kinetic friction. And so, again, these coefficients of static and kinetic friction are a result of our material properties, how rough or smooth the objects are. Okay, and so what we're going to do is, let's go step 7, change the surface back to wood, record the mass, coefficient of kinetic friction, and coefficient of static friction in the table below. And we're going to start with the small crate. So we need to reset everything. Go ahead and reset. All right, then we need to look at the mass. Well, the mass is, let's see, 100 kilograms. Okay, so 100 kilograms. And again, that's displayed at the bottom underneath the applied force bar, as it says right here. Then we have the coefficient of static friction. That's mu of s. That's 0.5. 0.5. Okay. Coefficient of kinetic friction is 0.3. Then we have our normal force. Okay, well, the mass is 100 kilograms. So F equals m times g, which is 100 times 10 meters per second squared. So that's going to be approximately 1,000 newtons. Okay, and if we wanted to calculate the maximum force of static friction, well, let's look here. Our acceleration due to gravity is 10 meters per second squared. And static friction, our maximum value, is given by this equation. So we say F is equal to mu of s times mg, and that must be equal to, therefore, 0.5 times 1,000. And so that's 500 newtons. All right, and so think about it. I'm going to do this last one, maximum of coefficient of kinetic friction. So that's friction. Kinetic friction is equal to mu of k times mg, and that's equal to 0.3 times 1,000, and that's equal to 300 newtons. Okay, and so this is a very long video, but I'm going to let you do these next two ones. Again, you're just getting these values from the bottom of the simulation. So after we've completed, so guiding question 7 is just to complete table 1. Question 8, though, we are comparing the value for the maximum force of static friction to the question in answer 3. Well, remember, this is from answer 3. The maximum force was 492 newtons, whereas our calculated our calculation for the maximum static friction was about Well, it was basically 500 newtons. All right, we got that from the table above. And so why is that the case? Well, this is the case because the force of friction, kinetic and static, is dependent on the normal force. And what is the normal force? Again, it's the opposing force between two surfaces. If you say, think about why aren't you sinking into the ground? The normal force is keeping you from doing that. Why does your hand not sink into a glass if you're holding a glass? Well, the normal force is keeping that from happening. It's the force that keeps your hand from penetrating the glass. It's the force that the chair keeps your body from penetrating the chair, okay? So the force between two surfaces in contact, that's kind of a repulsive force. All right, what do you think, what do you notice about the relationship between static and kinetic friction? So static friction has a greater maximum. Than kinetic friction. And then why do you think that might be the case? Well, that's an interesting question. There must be some sort of interaction between the surface, additional interaction between the surface of the ground and the bottom of the box. And so you could think that if you think of this as maybe like a rough surface against a rough surface, well, when they're just sitting there, perhaps it is able to really sort of press in and interlock with the surface below it, whereas as it's moving, it's not able to do that as much. And so overall, we see that static friction is greater than kinetic friction. All right, this is an exceptionally long video. I apologize. I'll try and break it up into 2 videos, but we have walked through the lab, and we see that static friction is our stationary friction force, kinetic friction is our moving frictional force, and static friction has a greater maximum than our kinetic friction. Okay, that's it for the lab.